Pretty. Chapter 8, 8.1 and 8.2 are, it's a quick section, and this is the whole chapter. We're gonna go over this, and this is the last thing before the test. So the test is next week. Um, Same deal as before. We'll talk about that more at the end, so it's not on the video, but 8.1 stuff actually isn't terrible. The formulas, the bad formulas are behind us. Like the ones we're dealing with now are, I don't want to call them simple because some of them aren't, but they're not like the other ones. I think the worst thing we have to do is divide and take a standard or a square root, which isn't terrible to do for either of those. So it should be nicer from here on out. All right, let me get rid of this because it's in my way. Let's do 8.1. That is pink, not ink. This is distribution of the sample mean. So basically, we'll, how do I want to say this? You're looking at a bunch of different means. So basically, how does our mean compare to the other ones we expect to get? Where does it fall in there? Is this a significant change from what we would expect? We're going to use z-scores again, and we know the z-score equation is very nice. So it's not terrible to think about these. Let me get some words down. Sample mean, and this is our X bar. So remember, X bar, our regular letters are for the sample. The Greek letters, so the mu, the sigma, those are going to be for the population. This is the probability distribution of all possible values of random variable X bar computed from sample size n. From a population with mean mu and standard deviation sigma. So our mean and standard deviation is important because we're dealing with z-scores again, and we need both of those to calculate a z-score. So really, we're just going to compare our data set to a population. We're also going to deal with a little bit, we know what our normal distribution looks like, ish. So ideally, our distribution of our samples is going to look normal. Everything works nicely, but sometimes it doesn't. Sometimes we're skew right and skew left. And the right and left part come from where the problem cases are. So the problem cases here are to the left, over here they're to the right. It pulls our pretty picture to that direction. So with the high skews, excuse me, the right skews, those are high numbers, numbers that are a lot higher than everybody else. Left skew, numbers that are a lot lower than everybody else. So we don't want that. Okay, I said slide 7 through 12. Okay. So we have an IQ test. Scores on this test are approximately normal. So we're going to treat them as normal with a mean score of 100 and a standard deviation of 15. What is the sampling distribution of the sample mean for a sample size? Um, Basically, what they're doing is they're going through and using tech to find a whole bunch of possibilities, and then we graph them from there. So we use our tech to find some different possible samples, and then we graph them. Not super exciting. Let me go through that. Couple important things, the shape of that. So we always look at, is it symmetric? Is the center where it should be? We know our spread, our standard deviation can make our graphs look a lot different. Is that my last one here? No, this is from later. So a thing to note, we can have the same distribution or same mean. So those are 3 different distributions that will all have the same mean. So the black one is kind of our standard, or what we think of our normal, for lack of a better word. The pink one says we have a lot of cases really near the center and very few that are far away. The green one says they're more evenly distributed. We have things are spread out a lot more. But those are all normal, so we have to kind of compare what we're thinking about with that. The last thing for chapter or section 8.1 is the central limit theorem. We don't talk about a lot of theorems in here. They're going on in the background. We just kind of assume them or state them in other words. So as the sample size n increases, the sampling distribution becomes approximately nope, hi. So the more cases we have, the more normal looking our distribution is. So ideally, we want as big of an N as feasible. We usually don't want our N to be the whole population because a lot of times our populations are huge and that's just not feasible to deal with. But an N of 100 is way better than an N of 10. And an N of 1,000 is even better yet. So the bigger we can get our N, the better our data is going to be. So another thing to note with this, if the distribution of the population is either unknown or non-normal, then the distribution of the sample mean is approximately normal divided. Oof, that was very bad. Let's try again. Somewhat better. Your N is at least 30. So we can make a lot of really nice assumptions if our N is 30. So we can use our Z-scores, which are relatively easy to use. We like them. Find our score, look it up on the chart. Remember the equation, hopefully. So what this really says to me is if you're looking at a study where they've done some math Purdue and have decided, hey, this is what our population looks like based on our sample here. And their sample size is less than 30, they're making assumptions they can't make. So you want your sample size to be a little bit bigger. You'll see you'll see some studies where they based it on like 5 cases and they're making big assumptions on 5 cases or something ridiculously small. That's not worth the paper it's written on most of the time, unless they're saying, hey, here are interesting things we found about this little group. Wonder what we'd find if we made it bigger. That's fine. But more cases is better in this. So we'll get to see a better idea of, is our mean different than the other ones? Is it significantly changed? Okay. That is really all of 8.1 is comparing our mean to the others. 8.2 gets a little more exciting. This is distribution of sample portion. I do not know why the word proportion is so hard for me to spell, but I always get mixed up which one is PRO and POR because it just does. So we're looking at we're looking at the fraction. I'll just give the equation. I made sure to write this word in my notes a whole bunch of times. This is our P hat X over N. Be careful not to mix up this P with probability because we're going to use that as well. We really like to reuse letters, but probability typically has a capital P and where your sample proportion is a little p. Is that for us? So our p hat is x minus n, where your n is your size of your sample. And your x is the number in a particular group we're looking at. That's really vague because it just depends on the example. We'll look at an example with that in a sec. Our population proportion. We use the letter P by itself, and its equation is the same, except we're going to use X over big N. Most of the time, we're not going to calculate our population proportion. It's assumed. So they'll say 15% of Americans think this. That's the thing we're comparing it to, is the assumption. for whatever, or old data or something like that. So like I said, we usually don't calculate that one, but we can. If they give you a percent, we want this in decimal. Door is so loud. It's easy to talk in percents because personally, I mean, I like decimals and fractions, but percents resonate the most with me. It makes the most sense in my brain. So we'll talk about percents, but when we do our calculations, we want to come back to decimal or fractions because that's what the equations are equipped to deal with. So we just have to go back and forth. So an example here. A survey of 1,200 Americans asked if they plan work while on a summer vacation. They found that 552 said yes. And let's pause for a moment and think of how sad that is that so many said yes, they were going to work on their summer vacation. I sadly would be one of those. All right, so if we want to find our p hat, so since this is a survey based on our data, we're going to use p hat. And this equals our group and our X is number who said yes. So X can be whatever based on the survey. This case, it's number who said yeah. So we get 552 over our 1,200. And this is a calculator problem if I ever saw one. That gives me 0.46. So sample proportion is one of the easier equations. We divide. Biggest thing is make sure you have the proper numbers and you don't button push the calculator wrong. Pretty straightforward. We're going to find the shape of the sampling distribution. I never write this word out, of p hat. So comparing all of our different sampling distributions is approximately normal when our n times our p times 1 minus p is at least 10. So this is something we should always check. Is this true for our data? So hey, does our sampling distribution follow this? If great, we move on, we pretend it's normal. If not, well, we don't. So if we look at our previous example, let's use their n. And we were given p hat here. So let's say that actual p was 0.6, just to make it a little bit different. I should put EX. So we want to see, hey, is this enough? 1,200 times 0.6 1 minus 0.6 gives me 1200, 6.4. I get 288, which is greater or equal to 10. So as long as our sample sizes are big enough, this is going to act normal. We're happy. Okay, so for a sampling distribution, the mean is going to be our population proportion. So that's what we're going to use. And that's mean of p hat. If it's not super clear, I can make that bigger. So we're going to use that. And if we want our standard deviation, and they use sigma of p hat, this is the worst of the equations we have, and it's really not that terrible. On these, we're going to have to calculate the standard deviation to get our normal distribution, but it doesn't take a lot. So little p times 1 minus p all over n. So that's honestly the worst equation in this whole section. And like I said, it's really not that bad. Not compared to the R equation. Okay, so let's say we have a population with a mean or a proportion of 0.76, and our sample size is 60. We're going to find our standard deviation. So sigma p hat equals, my p is 0.76, 1 minus p, 0.24, all over 60. All right, 0.76 times 0.24 divided by 60. Whoops, I wrote times. This gives me a very tiny 0.00304, and there's probably more decimals, but I'm not going to write them down. Square root that bad boy, second square root. I get 0.055. Be very careful with these numbers. I would leave them in your calculator and just keep calculating on top of it rather than retype them in, just because there are some hidden decimals there I didn't write down, but my calculator is going to show them most likely. If you don't, you're going to get some errors because you'll be off by enough that it'll get mad at you. So just be careful on those. All right. Hopefully that is good. Let's look at, nope, come back here. Slide 56. Oh, no, they're going to give away the thing. Okay. This was not as depressing of an example as some of them are, so we're going to use that. So according to the National Center for Health Statistics, 15% of all Americans have hearing trouble. And a random sample of 120 Americans, what's the probability at most, 12% have hearing trouble? So I said my N is 120. Our population proportion, or our mean in this case as well, is 0.15. And we want the probability that, at most 12% have hearing loss. So this is 12% or less. If we were to draw this out, which always helps in my opinion, our population mean is 0.15. And 12% turns into 0.12. So this is less than the mean. Your data value is going to be here-ish. And we want the percent of that or less. So when we draw out our normal distribution, it tells you where to shade, here or less. This also tells you what to do with our chart. If we have the here or less, we just look at our chart, grab the number, and we're done. The other two cases, between or more, take a tiny bit more work, but this one's the nice one. Okay, so how do we find that? Well, we're going to need a z-score eventually. So we need a z-score, and to get that, we need our brain standard deviation. So sigma equals square root, and our equation was up there. Our actual p, which is 0.15, times 1 minus p, 0.85, all over our sample size, 120. Throw that in my calculator, and I get about did I write this down? 0.33. So threw it in my calculator, that's what I get out. So our z-score, in this case, we're going to use our p-hat minus our mean, which is our p-value, all over our standard deviation, 0.033. Our standard deviations are always going to be decimals here, and probably small ones at that, because we're looking at proportions, which are always 1 or less. So we get some little numbers to deal with. So that's our generic our z-score equation. Our z-score is going to be 0.12 minus 0.15 all over 0.033. That gives me, gonna write that down. Oh, it did. Look at me. Negative 0.91. Find our z-score. Now we want the probability that at most that has this 12% or less. Probability that at most 12% have hearing loss. Wow. So we have our z-score. Now we're going to look up that probability. So negative 0.91, we go to our z-chart, which is here. We go to negative 0.9, which is at the very bottom, sorry. Go over 1, I get 0.1814. What I look up is 0.1814. So the probability that at most 12% have hearing loss is 0.1814. So there's our whole, this part of the problem. I'm gonna sum up our steps because it feels like there's a lot of stuff everywhere. So steps. Identify the things we need. So find your N, your P hat. If you have a standard deviation already, great. If not, we calculate that. If they don't give you P hat directly and you have to find it, step 2 would be to find that. But definitely calculate your standard, your standard deviation. 3, z-score. So we get z equals our P hat minus our P over standard deviation. Should probably have done this before. Say this one above. Side. Either score or less. Score or more. Or between two scores. So it may help to draw the picture of what you're looking for. I always found it did because I'm visual. I like pictures. So decide what we want. And then that's going to help us with our z-score. Look up z-score. Last step. Subtract if needed. Translate into so I say subtract as needed. If we need this score or more, we take 1 minus whatever we looked up. If it's between two, you subtract the bigger one minus the smaller one. If it's the score or less, we don't subtract, we just look up. So depending on what they're asking us, we may look up or not. And remember, we subtract the value we look up, we do not subtract our z-scores. We can't compare z-scores in that way. It would be nice, but alas, we cannot. And the last thing we should do is, what does this mean? So put it back into more standard spoken word. Now, what does it mean? Why do we care? Does this find us the thing we're looking for? Is this a rare occurrence? Is this non-rare? What are we looking at? All right. What else did this example have? Okay. So the next piece of this is, so suppose our sample um, 100 or 1200, no, 120 Suppose in our we have 26 with hearing issues. We know our P from before, so let's say we have P equals 0.15. Our N is still 120. What is our P hat? Well, we take our 26 over 120. 26 divided by 120. 0.22, let's call it. So let's see what that means. So we have a higher population, our proportion is bigger than the general public population percent or proportion. So let's look at that. What's the z-score of that? We have 0.22 minus 0.15 all over, what was our standard deviation? 0.033. Five divided by 0.033 gives me 2.12. Okay. So look up if z equals 2.12. Our area to the left is here. That is going to be a really big number, 212. So there's 21012, 0.9830. If I were to graph this, my z-score is positive, and it's going to be over here. So let's shade that in. So now we get to translate this into real words, which is honestly the hardest part. What this is saying is our group here, the probability we get a group with 26 out of our 120, and hang on, I'm saying this wrong. The probability that a group has a proportion of 0.22 or less with hearing loss is 0.9830. Group of 120 has more than 6 with hearing loss is so the probability we get a group with more than 26 is 1 minus the number we looked up. So this would be 1 minus 0.9830. I do not have that number. 1 minus 0.9830. So that says less than a 2% probability that our group is going to have more than 26 people in it. So our group of 26 is weird. That's higher than our average, so by a lot. Most groups are going to have that or fewer. So we have a weird group. It's kind of what that means. We can't make a lot of assumptions on these because we're just comparing our population, but we can say, okay, is this normal? Do we think that this is standard, or is this abnormal? Do we have a lot higher than we would expect? And at that point is a good question of why. Why do we have a weird group? So I'll come up with some reasons. In this case, maybe there are people like my child who likes to put their headphones on max volume constantly, and that has ruined his hearing. Or it could be you've got a bunch of people who are older, who have worse hearing than younger. So kind of look at the reasons why at that point. All right, this is all of our chapter 8 stuff. I'm going to stop the video and then talk about the test thing. I don't want those on the video because I'm hoping to reuse these for other semesters. And that is that.